we are going to start the lecture on nanotechnology in chemical engineering. So, today we will discuss various properties of that nanomaterials that we will prepare. So, here already we have discussed about the properties of the nanomaterial, that is physical, chemical and biological properties. So, out of that physical properties, various surface area, melting points, catalysis properties, thermal properties and mass transfers, defects, these are the things we already have discussed in our previous lecture. So, today we will discuss about the mechanical properties of that materials, nanomaterials that we are prepared, electrical properties, optical properties and magnetic properties. So, these are the things very means whatever the materials we will prepare, that may be iron based materials, cobalt based materials, nickel based or whatever the materials. So, in nano form, so that having a particular property. So, that properties is useful when we prepare that materials, how good that particular property, if it is useful for that particular preparation. So, here first we will discuss about the mechanical properties of that material. So, depending upon the material properties, we can say that the elasticity, tensile strength, hardness and flexibility of the materials, means once these are the property we can means able to identify or we can measure that particular materials whatever we have prepared. So, using those properties, so we can say that they have to useful that particular nanomaterials good for that particular applications. Okay. So, here once we use for a particular metal, let us say irons or steel whatever we have prepared. So, here different type of others non-metals also component is present, that may be carbon, oxygens or whatever. So, that present. So, then the property of that materials will be mechanical property will changes. So, also the size of the materials, that is if we bulks to nanoscale. So, then the materials will change from a large size to the smaller size. Therefore, materials that will be changes into single crystalline materials that will be changed. Okay. So, depending upon different type of nanomaterials, we can say that that particular specific property is present. So, here you can see that nanoparticles, nanorods, nanotubes or nanocrystalline solids. Here you can see that here and the granular thin films that is present or coated over the surface of that materials, over homogeneous thin films also, that is, and multi layers also you can see here 1 2 3 4 5 6 any number of layers that materials we can prepare. So, depending upon our applications. So, once we prepare that material, so then we need to see the property of that material. So, that one kind of here list of materials is showing here. So, here Young modulus, that is was measured for that particular material. So, that is very important property for that mechanical property, that is Young modulus, that is expressed in terms of stress by strain. So, depending upon the materials whatever we have prepared, if we use various type of nanomaterials in that this particular property means Young modulus of this crystalline nanocrystalline materials will change. Okay. So, here when the grain size of that materials that was prepared. So, let us say magnesium nanocrystalline materials. So, grain size when 12 nanometers, the Y, that is Young modulus, that is 3900 Newton per square. So, when it is bigger size means more than 1 micrometers, that Young modulus of polycrystalline materials that has been increased. Okay. So, similarly another example, that is palladium nanocrystalline materials that has been prepared. So, and its grain size is 8 nanometers. So, then its Young modulus is 8800 Newton per squares. So, when it is polycrystallines, so when the grain size is more than 1 micrometer, so then it has been increased to this. So, depending upon that materials and its grain size, the Young modulus, so that would change. So, depending upon our applications, so we can see that particular properties whatever the materials we are prepared, its grain size, and then we can characterize that materials based on that particular properties. Even plastic deformations also. So, that also we can see, suppose we have prepared in nanocrystal materials. So, we can say that when it is nanocrystallines or polycrystalline materials, depending upon their plastic deformations also we can characterize that materials also. This is one another property. So here you can see one nanocrystalline materials have taken, one polycrystalline materials, that is both are made of nickel materials. Okay. So here it was made nickel material. So here stress and strain if we plot, so then the plastic deformations I said. So you can see that is up to this, and so when it is polycrystalline material, so it is like this. So stress strains whatever that present in that particular material, so depending upon whether it is polycrystalline or nanocrystalline material, so depending upon that materials, that plastic deformations also, that particular property also change. Okay. So another one is the hardness of the material, so that is the related with the grain size. So if we use nano size or micron size of materials, so here one example is showing here copper, that materials was taken. So its grain size is micrometers and nanometers. So if we use micro grain size, then hardness that which decrease with the grain size. Okay. So when it is nanomaterials, that grain size is in nanometer range, so the hardness increase with decreasing the particle grain size, that is linearly. So if we increase the grain size of nanomaterials like this, so then that hardness that would changes like this way. Okay. And in case of the micron size, so this way it would change. Okay. So depending upon that materials, whether it is nano or micro crystalline or grain size, so depending upon that the hardness of the materials will affect, that will change. So that depends on that materials we have prepared and its property. So another one is examples I can show here, the mechanical properties of CNT, carbon nanotubes. So that its property, it is much more stronger than steel materials, it is 100 times stronger and 6 times lighter, so as compared to the steel. So this property means we can characterize that materials we have prepared and its property. And next one is the electrical property, that is also very important property. So whenever the materials we have prepared, means this is the basic things what is called electrical property. So means whether the materials is conductors, semiconductors or insulators, so depending upon band gap, so we can characterize those materials, whether the material is conductor, semiconductor or insulator. So there is the energy separations which is called EC. So valence band, conduction band, these are the things we need to know. So when we know about a particular materials, either these three different types of materials. So in case of the conducting materials, we know that the valence band to conduction bands, the band gaps or energy that is very small. So that having showing the metallic properties, then it is called conductions. This is conductors. If it is gradually increased, then it is called semiconductors or insulators. Okay. So whatever the nanomaterials will prepare, so we can see its electrical properties, and depending upon that we can say whether it is conductor, semiconductor or insulator. Sometimes we can prepare any metallic nanomaterials. So if we add some others non-metal components, so then the metallic property of that metals will change. So metals will convert it into semiconductor or insulator materials, or some insulator material, let us say ceramic materials we have. So if we add some metallic nanoparticles with that, so then some conductive properties of that materials will change. Okay. So insulator, that may be semiconducting or conducting property that we can grow or we can develop in that materials. Okay. So here some exceptional material, that is fullerenes or CNT, that we will discuss later. So it has some exceptional electrical properties. Okay. So these are materials that has, or that material possesses exceptional electrical properties. So next is the optical property, that is also another property that we can, means whenever we prepare a material, so that property also we can see, or we can changes the size of that material. So we can changes its one particular property, means optical properties. Suppose it is bulk materials, that is converted into nano size, so then its property would be totally different. Nanomaterials and bulk material both are different, optical properties also will be different from different. So here one example means how we can see a materials colorful. So that is when that is reflected that particular spectrums. Okay. So whether it is colors or whatever the color, so that we can see. So here's one example I will show. Here's CDAC, that quantum dots, that materials, very small dimensions we can prepare. So it is, if we changes its size from our dimensions, so then it can show different optical property, means blue to red. So blue to reds, that would change. So depending upon its size. So if we change its size, a particular dimension to the another dimension, so then it would show different type of colors, and that materials we can apply a specific applications where a specific size of the nanomaterials is required for this applications. Okay. So here's another one is sunscreens, that is zinc oxide titania clusters. So we can prepare these material zinc oxide titania clusters as a sunscreens we are using. So its size may be 200 nanometer, 100 nanometer, or less than 50 nanometers. Any size we can prepare that nanomaterials. So whence it is, let us say 200 nanometers, it is, or it appears as white colors. Okay. So whence we changes that clusters 200 nanometers to 100 nanometers, means the nanoparticles size or dimensions we are changing. So reducing the cluster size 200 to 100 nanometer size. So then initially I said it was appear as a white color. So then, so when its size is reduced into 100 nanometer, 200 nanometer to 100 nanometers, so then it would appear as a transparent. So white to transparent, so that is property this particular type of nanomaterial it has been shown. So then means this way we can change a materials in different larger particles or larger size to smaller crystallines or smaller size nano range. So then its property apparently would be changes, and then so that would be applied to a specific applications that would be useful for that. Next is the magnetic property. So different type of materials we can prepare, so that I said metal oxide. So it has also having magnetic property, that is one important property whenever we study the nanomaterials or nanoscales applications. So this property is also very important, so that we need to know. Okay. So in magnetic properties, so when a materials, whether it is different type of magnetic materials we can classify, that we will discuss. So this is called magnetization curve. This curve is called magnetization curve. So when we apply magnetic fields a particular strength in that particular materials, if that materials changes are there by applying these fields, it would develop some magnetic properties. So then this type of curves we can get. Okay. So this is applied fields and this is magnets that we, means initially this was like this way. If we increase the fields, it would gives ms, and then if we down the field, so then it would move to this, means in this materials initially there was no magnetic property, but once we decrease the fields, so then some magnetic property will be there inside of that material, that is such that magnetic, means depending upon this magnetization curves we can classify or characterize the particular materials up to what type of that materials that we have prepared. Okay. So I am not going to discuss about this particular field. So here the magnetic susceptibility, that is expressed in type this. So it is the ratio of these magnetizations and field strengths. So it is, means if you know this value, so then that property of that materials we can say. So here's x xi versus temperature. So depending upon that, so a particular type of materials, whether it is diamagnetics or ferromagnetism, paramagnetism, antiferromagnetism. So depending upon that nature, so the temperature versus this magnetic susceptibility, so we can get that particular, or you can say that that materials is like that. So depending upon the type of ordering of that arrangements of lattice ions and spins, so we can classify that magnetisms 5 different category. So diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. This type 5 types of magnetic materials, or the materials, whatever the materials, that is nanomaterials we are preparing. So these 5 way or 5 categories we can classify materials, and based on their magnetic properties. Okay. So here you can see that this is called lattice ions and its corresponding spins, that arrow indicate that is the spins and circle that is lattice ions. Okay. And this it is randomly distributed in that particular materials, then it is called paramagnetism. When it is alignment is particulars orderly, so aligned to the same directions. So here you can see it is ferromagnetism, that material property is ferromagnetism. So when it is anti-ferromagnetic, so one line is this directions, another line is opposite directions. So then alignment is means one is same direction, another is opposite directions of the lattice ions and the spins. So then we can anti-ferromagnetic properties of that materials. Another one is the ferromagnetism. One is it is similar like that anti-ferromagnetism, but here one is these directions that spin, another in opposite directions, but spin is strength is different. Okay. So one is smaller, one is the larger. So depending upon that also we can classify or categorize that materials. So here this point is called MS, saturation magnetization points. This point is called remnant magnetizations points. Okay. So and this particular point is called that particular point. So whenever this is magnetization curves is there, so these are the three particular points MS, MR, AC. These are the components we need to know, means depending upon that materials whatever we have prepared, so it would change. Okay, depending upon the magnet materials we have prepared, its magnetic properties, that locations of MS, MR and AC will change, and then we can classify or characterize that particular material, is whether it is paramagnetic, ferromagnetics or antiferromagnetics, diamagnetics, whatever the materials that we can see or we can classify. Even these magnetization curves, here you can see MH curves, when these hard magnetic materials we have, so then or it is permanent magnets, so then this type of means you can magnetization curves you can see like this. Okay. So here coercivity was 1T, and so whence this is lower coercivity, so then or lowest coercivity. So this type of three different way we can means see image curves depending upon that materials. When it is soft magnet, so then this would be soft magnet, this is permanent magnet, this is soft magnet, and hard magnet you can say this is hard magnetic materials, this is soft, and this is a magnet is very low coercivity. Okay. So that way we can means see by seeing the image curves we can classify that materials whether up to means what type of magnetic property is present. So here's now these applications oriented means the materials having this particular magnetic property, it depends on the size, shape, compositions and cell core designs. Whatever the nanomaterials will prepare, we can prepare it various size, means 100 nanometer, 50 nanometer particles, 20 nanometer, 10 nanometer particles. So if we prepared a different size of materials, component compositions or material composition is the same, but size is different, then its magnetic properties will be different. Even shape, that materials whatever we are preparing, so that may be cylindrical shape, triangular shape, spherical shape. So depending upon that also the magnetic property will change. Even composition, suppose you have prepared a material that is made of irons, if we add a percentage of cobalts or nickels or any other components, so that metal oxide composition should be changed. If we change different percentage of that second metal or metal oxide, and cell core designs also, that also affects. Let us say any metals we have used metal oxides and it is coated with or outside coated with silica or any other material, so then its property, magnetic property will be changed. So this magnetic properties of the nanomaterials, it can, I said many way you can apply, sensing, drug delivery, hyperthermia, many applications, biomedical applications it can be used. So the influencing parameter is size, shape, compositions and cell core design. So these are the things whenever we prepare a material, so we look into that, and depending upon that the materials will change its property, and depending upon that we can prepare that materials depending upon the applications. We can prepare that materials having that particular tunable property, and then we can apply that. So, okay, so here's particle size is very important. So how we can say that? Here's a list of materials: cobalt, nickel, cobalt, platinum, iron, platinum, iron, cobalt, Fe3O4, Fe2O3, cobalt, iron oxides. So here's you can see when that materials whatever means particle diameter is very important. So when it is larger diameters, so here multi domains region, single region and super parameter region. So whence it is diameter changes less than 0, then the materials will behave super paramagnetic property. When it is lower than this RC particle diameters, then it would show single domain regime, and whence it is above that it is multi domain regime. Okay, so here's means this one these curves it shows the transition from super parametric to the single to the multi domain regime, and here this is maximum diameters and single domains, multi domains are the materials we can change. So here single domains, that is black. So up to these diameters if we able to prepare this material, so then this particular material, so that would show single domain. So after that it would show paramagnetic, super paramagnetic properties. So even in case of the nickels also, up to these diameters it would show single domain, and then if it is able to prepare the nickel materials lower than that diameter, so then it would give super paramagnetic properties. So like that other materials or metal oxide component also, that would show different type of properties. So here the critical size means that materials means where the materials is show different type of property, that depends on that I said the particle diameter. So means different size of the materials or nanomaterials, metal oxides we can prepare, and a particular size is very important. After that the materials will show single domain, multi domains regime, or once we reduce or go lower than that diameter, so then that would show super paramagnetic regime. Or here's 1 2 3 examples will show how the size of the materials means Fe3O4, let us say we have prepared. So if we decrease the size, then MS property, saturation magnetizations, that would change like this way, coercivity also will change like that way. If we prepare these materials cobalt and iron based nanoparticles, if we increase the size 2.8 to 6.7, then saturation magnetizations of this also will change. If we increase the size, saturation magnetizations of that materials will change. Okay, so image curves that we will see, so they are also means all these three type of different size of materials we can prepare, we can check that its property will change. Okay, similarly cobalt iron oxides we can prepare, that is magnetic nanoparticle. It we can prepare in the form of sphere or can prepare it cubical. So if it is sphericals, MS in or sphere both are same, but coercivity will be different. In both cases spherical materials coercivity is 16,000, when it is cubicals 9,500 coercivity we can observe. Similarly others materials also, that property MS property or coercivity, these are the property changes. Okay, so effect of compositions of magnetic on magnetic properties. So here you can see all nanomaterials that is based of iron, manganese, cobalt or zincs with irons, others metal oxide also impregnated, okay, by using different precursors. So initially base component is ferric oxides, with that others components we can use manganese, cobalt or zinc, and all are having the same particular size 200 nanometers, but MS property you can see that would change, means depending upon the metal nanoparticle compositions the MS property will change. Okay, even I said the cell coats, various type of coating also we can put about that materials and magnetic nanomaterials that we have prepared. Let us see Fe3O4. So it has particular size 5 nanometers, MS property is 72. So here's if we coated with silica, means if we prepare that core cell models, that materials if we are prepared, so then its sizes will increase and then ms property will reduce or down. So means both are having same materials, magnetic material Ap3O4, but due to the coating of that materials, means that materials have been prepared, so we can down the ms property. Okay, so this way we can prepare a type lot of material, nanomaterials, and depending upon that materials component compositions, particle size, diameters, compositions, so that particular property will change. Okay, so today is up to this. Okay.